Hi everyone, welcome to the first of the Stormwater 360 webinar series for 2023. Our webinar today is the hydraulic design of manufactured treatment devices, and I'm Matthew Howes. I sit within the sales team, and I'm joined by our senior technical engineer, Kevin Jonathan. This webinar we ran at the beginning of last year, and it was one of our most popular webinars of the year. So it's our pleasure to bring it to you again today. A little bit of housekeeping rules. We'd love to have some questions, and there is time set aside at the end for questions. If you have any questions at any point in the presentation, please write those in the chat area of the Teams meeting, and then when we get to the end of the presentation, we can run through that and answer those questions with you. You should all be able to hear and see us, but at any time, if you struggle with hearing or seeing us, let us know, and of course, make sure that the volume on the computer is turned up. So without further ado, let's get into it. So, the hydraulics of proprietary treatment devices. A little bit about Stormwater 360. We are a company that has specialized in stormwater treatment and the effective stormwater management since 1996. Mike Hanna and Greg Yeoman started up the business in 1996, and we have 26 years of dedicated expertise in managing stormwater. I'm Matthew Howes. I primarily work at the moment within the Waikato region, as well as across the country in the sales team. And Kevin heads our engineering team. As a company, we're focusing on good quality solutions, and good quality solutions for stormwater require good quality engineering practices. So we're very proud to have quite a large engineering team to support the designs that we offer. Little bit about the presentation and what we're going to talk about today. It's important when we understand the hydraulics of proprietary treatment devices that we understand basic hydraulic principles. We understand what driving head means, what elevation head means, and the difference between the two. What does headwater and tailwater mean when looking at a treatment device? And how do we manage and define peak flows versus treatment flows? And for each of these hydraulic terms, we're going to then explain what they are and then apply that to proprietary treatment devices. And we're going to talk about how do we, as Stormwater 360, how do we design with this in mind when we get approached to provide a solution for a site. I think first, though, it's important to recognize why we treat stormwater. Why do we put in these structures, these devices, whether it's a proprietary device or a rain garden or a wetland? Why do we put these in place? This is a photo of the inside of a storm filter on State Highway 16. And without any treatment structure, all of that would flush straight to the Waitemata Harbour. So there is an awful lot of contamination that can run off our sites, not just the visible, but things that you can't see. So when we work out, well, what type of treatment do we need to provide? We think about and broadly categorize the types of contaminants by their particle size. So oils and hydrocarbons, we generally try and separate from stormwater. And then litter and trash is generally about greater than 5 millimeters in size. Then we have coarse sediment. Sediment itself spans a range of different particle sizes, but coarse sediment is typically 110 microns or 0.11 millimeters and greater. And then there's fine sediment. Fine sediment typically has a median particle size of 75 micron, but can go down to as low as 5 microns, depending on the soil conditions and the sediment from the site. Then you have metals and nutrients, which can take a number of different forms, both particulate and dissolved, and you have to consider what type of state those contaminants are in when you're treating. So for each type of contaminant, there is a type of treatment mechanism that best provides treatment to address that contaminant. So for oils, we try and divert. For litter is around 100% of trash capture. For coarse sediment, we typically use settling or screening gross pollutant traps. Fine sediment requires a filtration device, whether that's a media or a membrane filtration. And then metals and nutrients typically require an enhanced level of treatment, especially if you have dissolved metals or dissolved nutrients. So for each treatment outcome, there are then a range of ways to address those contaminants and a range of different treatment devices. So how do you go about working what treatment device to provide? Well, there are water quality guidelines within New Zealand, and the water quality guidelines that are around both regional councils and district councils, they provide you with an outcome that we need to achieve, but none of the guidelines specifically reference how to design and how to integrate a proprietary device into your stormwater network. So it's really important then that we, in addition to the guidelines that are given, we consider the impact of treatment device on the hydraulic nature of the network. So back in 2016 for the Stormwater Conference in Nelson, Kevin here wrote a paper on the designing stormwater treatment devices, resilient considerations and implications. And this goes into quite a lot of depth when you're looking at the different characteristics. But one of the key things to consider is that Stormwater 360 and other devices that are available use gravity and water flow to provide treatment and provide the treatment mechanisms. So generally speaking, you don't pump treatment devices. There's no electricity. They all use the flow of water to start and continue the treatment mechanism. So the correct hydraulic integration of those devices into the network is key to ensure that the device is going to treat as you need. Kevin's paper goes into a lot of detail, and tomorrow when we send out a link to the recording, I can also include a link to the paper. But for now, I'll get Kevin to talk through some of the basics of hydraulics.
Thank you. So we're just going to go through some of the basic hydraulic principle. And you're probably quite familiar with a lot of these when you're designing a reticulation system. But just remember that designing a treatment system is pretty much the same as designing a hydraulic node or hydraulic structures. So the consideration stays the same. As you can see on the presentation there, one that we look at is the continuity equation, which is flow is a byproduct of velocity and the cross-sectional area. And next is just the energy management that we use for flow in pipes, which actually just really show the energy upstream is equal to the energy downstream with additional head losses. And next is the hydraulic gradient, which is the change of hydraulic gradient over the change in length, which you can apply in either horizontal plane or vertical plane, as you can see there. Next is the Darcy's law, which is how to calculate the hydraulic head required for flow of fluid through porous media. And next is more just an application of the continuity equation on the orifices and also weirs, in which here all we're doing is just applying the coefficient of discharge to the formula. But again, it is really just a byproduct of the velocity versus the cross-sectional area. And really what's the most important here to take it out is if there's more heat, means there will be more flow. Less heat means less flow. Next is the head losses, and you can see here that head losses occurs through flow from network, and which occurs from friction on the pipe walls, bends, sometimes even losses through entry and outlet of pipes. And these head losses reduces the velocity through the pipe, and it increases the hydraulic head required to convey the flow through the network. And on the right, you can actually, the graphic on the right, it shows the effect of the tailwater on the headwater in reference to the hydraulic structure. So now Matt will go through, we're going to apply all these basic principles, and we're going to put it in a context on designing the treatment system and what you actually need to consider.
So proprietary treatment devices can be used to achieve water quality outcomes. They're obviously not the only way to do that, but they are a good way where area is tight, where there's not room, say, for a large pond or a wetland. They provide useful outcomes. And so for each level of treatment that we talked about for the different contaminants, we have a range of treatment devices that sit and provide that level of treatment. The reason for having a range for each type of treatment, so for pre-treatment, we have 3 GPTs because not every site will be able to accommodate the hydraulic restrictions of one treatment device. So having a range allows us to fit into more sites. But for the purposes of this webinar, we're going to consider 3 treatment devices primarily. The first is the cascade separator. That is a hydrodynamic separator designed as a pre-treatment device to capture high percentage of coarse sediment. The next is the jellyfish. The jellyfish is a membrane filtration device, treats down to as low as about 5 micron particle size, very high flow rate, very low driving head. We'll find out what that means shortly. But is really useful for particularly tight sites. And the storm filter is one of the most ubiquitous treatment devices in New Zealand. Sizes for the storm filter go from 1 cartridge up to 580 cartridges, and it's been used throughout the country to great effect. So when we get approached to be asked to provide input into the treatment design for a project, we will ask a few questions. We'll ask what the treatment requirements are, and that tells us the type of device we need to choose from. We'll ask for the catchment areas and what the flow rates are. We'll ask for the available depth to invert, both for the inlet and outlet. We'll ask if there's any driving head constraints, and we'll see if there are any upstream or downstream water surface elevation constraints. And the reasons why should become apparent shortly.
So here, the elevation head, or sometimes quite known as the physical drop, it is really defined as the difference between the inlet and outlet pipe across the hydraulic structure. But a lot of people misunderstand this to be the total driving head of the treatment device. Now, as an example on the right, you can see the elevation head. If you could type, yep, the elevation head is represented by delta Z, but the total driving head is actually represented by the delta H. So if you actually take the delta Z as your total driving head, then this could cause an unintended surcharge to the upstream network, which could actually cause flooding. So Matt will actually take you through some of the application of this difference between elevation head and total driving head through our treatment system.
So for the cascade separator, the way the cascade separator works is it dissipates energy within the water to allow sediment to settle out. So it's quite unusual in the fact that the outlet invert, as shown here on the drawing, and the inlet invert are at the same level. So with the cascade separator and with the vast majority of gross pollutant traps and GPTs, there is no physical drop through a cascade. So if we look at the jellyfish filter works as water flows in, goes down into the sump that is there, and then flows up through those membrane filters and then out through the outlet. So relative to the outlet invert, which is shown here on our drawings, we have the inlet invert, so outlet to inlet. as standard on the jellyfish, the inlet is 150 millimeters above the outlet, but that range varies because the jellyfish uses an upflowing treatment mechanism flowing up through those membrane filters. You can have a bubble up situation through the jellyfish. So the jellyfish can be used in a bubble up configuration. With the storm filter, again, the outlet invert with the storm filter is pretty much at the base of the sump, so there's minimal depth below outlet. And there is a range of inlets that we can have. So from the outlet, as standard, you might put the inlet, say, about 770 mil above the outlet, but there is a range with the storm filter, anywhere from 30 millimeters full through a standard manhole configuration up to 770 mil. So there is a range of elevation head physical drop that you can have with and through treatment devices.
Cool. So another type of heat is the driving heat. It is commonly known as the hydraulic heat. It's just a measure of mechanical energy caused by flow. You can see that's represented by the formula there. But all it is just a differential of upstream and downstream water surface elevation across a hydraulic structure. Now, driving heat is probably the most important component when you're designing a treatment system, as all treatment systems will require a driving heat to operate its treatment mechanism. So if you don't allow sufficient driving heat, the system will not treat to its design flow rate. And worst case, it actually will prematurely overflow the contaminated stormwater without treating it. And now Matt will go through some of the driving head application on our treatment system.
Yeah, and it's important to remember that driving head and physical drop are two independent things. Then they are, there are relations, but they are independent. So if we think about the cascade separator, so within the cascade separator, there is a depth below outlet invert. So there is a sump of water, permanent water level within the cascade, and water flows into the device, and then it needs to build up behind that weir that is part of the treatment mechanism, and then it overtops the weir and flows out. So the driving head is essentially shown here. And with the cascade, because there are a range of different sizes, and essentially it is a similar process to head losses across a weir, the driving head for the cascade varies on both the device size and the treatment flow rate. So that's something where suppliers should be able to give you the driving heads for different flow rates across something like a GPT. With the jellyfish, again, there is a depth below outlet invert, and that is, again, a permanent water level within the sump. The driving head is shown here on the drawing. So water builds up behind the maintenance access wall, and then that is the driving head required to push the water through the cartridges at a predetermined flow rate. With the jellyfish, the driving head is measured from the outlet invert. So it's measured from here, and it's the level the water has to get to for that device to operate at the design treatment flow rate. And that is typically controlled by an upstream weir. As standard, the jellyfish can operate with a head of 457 millimeters. We can go down as low as 150 millimeters in certain circumstances. So the cartridge size and the driving head with the jellyfish independently affect the flow rates. Now, it's important as well, we said that driving head and physical drop through the device are separate. With our outlet invert here and our range of inlet inverts, regardless of where that inlet is, we still need that water surface elevation to push the water through the filters at the design treatment flow rate. So if there is a bubble up configuration, the water surface elevation inside the jellyfish will be higher than the inlet pipe. Same looking at the storm filter. The storm filter, the driving head is shown here, and that is the water surface elevation required for the floats within the cartridges to pop up and that siphon to start going. So again, we have a range of different cartridge heights that have a range of driving heads. As standard, the 69 centimeter cartridges have a driving head of 770 millimeters. The 46 centimeter cartridges have driving heads of 540 millimeters, and the 30 centimeter cartridges have a driving head of 380 millimeters. This means that if the side is particularly tight, we can use a shallower cartridge to fit in with the network. The one downside, however, of using shallower cartridges is they have shallower driving head, so you can't get as much water through the cartridge as if you had a higher driving head. So switching between 69 and 46 centimeter cartridges, you'll need an increased number of cartridges and an increased footprint. And then if we compare with the storm filter, that outlet invert and the range of the inlet inverts, no matter where that inlet pipe sits within that range, we still need the water to build up to that level for the device to operate. So even with 30 millimeters fall through the storm filter, we might still need 770 mil of driving head.
So another type of water is the headwater, also known as the backwater. Now, this is the water surface elevation upstream of the hydraulic structure. So this typically happens when there's downstream restriction, like an orifice or a weir, but it is actually promoted or used by volume-based treatment system like a pond or wetland that relies on energy dissipation and low velocity for the sedimentation to occur. The example here is a hydrodynamic separator. It's a vortex that uses that orifice and weirs to quickly raise the water level, which then reduces the velocity and promotes the sedimentation inside it. So it is important to remember that when you are creating that backwater, it will actually surcharge your upstream pipe. Now, from the previous example that we looked at, where the physical drop between the treatment system is the delta Z, but the total driving heat is actually that delta H. So you will cause a surcharge to the upstream network, and that is the difference between the delta Z and delta H. And there's of course there will be some head losses as well on the pipe friction, and depending on how many hydraulic structures it goes through surcharge upstream, they will cause additional head losses as well. So another one is the tailwater, and this is defined by the water surface elevation from downstream of the hydraulic structure. So there's two types of tailwater. One is a permanent tailwater. The other one is the operating tailwater, or more of a temporary tailwater. So here with a permanent tailwater, that's typically caused by a natural water body like a stream or lake, and it can sometimes be caused by a bubble up structures or permanent water through the network. And a temporary tailwater, as we see before, can be caused by a detention tank downstream, or even just a depth of flow in the pipes. Now, tailwater is a really important consideration when you are designing a treatment system, as it can directly affect the available driving head by reducing it, and that will reduce the maximum treatable flow rate, and it won't achieve it won't be able to treat it what it was designed for. So now Matt will show you how tailwater can affect the treatment system.
So if we take, for example, the storm filter driving head is measured from the outlet invert level, and that assumes a free discharging pipe. So that is the difference between the outlet invert and the water surface elevation within the device required for those floats to pop and the treatment device to operate at the flow rate that it has been designed for. So that is then the driving head. If then there is tailwater that is acting upon the treatment device, whether that's from a swale or down a stream that is downstream, whether it's from a detention tank that's fulfilling SMAF requirements, that will reduce the effective driving head of the device. So although the water surface elevation has been met and the floats have popped and the device is operating, the driving head has been reduced by the amount of the tailwater. So the effective driving head then is no longer 770 millimeters. So operationally, as Kevin alluded to, that reduces the treatment flow rate from the reduced effective driving head. And it can mean that the system may prematurely bypass before treating the full first flush. And the water quality flows might not be treated to the extent that we are expecting. If you have to design with an operating tailwater, you might have to accommodate reduced flow rate per cartridge, therefore needing more cartridges to treat the same flow rate and a larger device. The other issue with having an operational tailwater is that water for all treatment systems is designed to flow one way. It's designed to come in, be treated, and then flow out. And if we have water back flushing through the treatment system, that can lead to resuspension of material, sediment, contaminants that have previously been settled out from the water. Another quite significant issue with tailwater is that it can impact the maintenance of the treatment device. If there is prolonged saturation, so for an extended drain down time of a couple of days, let's say, prolonged saturation of the media, and especially the perlite media and the storm filter media, can lead to biofouling. That can then also lead to premature clogging of the treatment device and the requirement for maintenance to be carried out at more regular intervals, so increasing the number of maintenances required in a given time frame. This is also important to consider for green infrastructure, whether it's a rain garden or our Filtera, the high-performance biofiltration system that we offer. There is still a physical drop through the device. There is still an effective driving head. We still have to consider how we manage the peak flows in a green infrastructure device. And tailwater, again, will reduce the effective driving head of this device. One other important consideration with green infrastructure is that tailwater and or a permanent water level within the system can cause issues with nutrient release from organic matter within the media. Things like nitrogen and nitrates, they have very different removal mechanisms to phosphorus and phosphates, and having an anaerobic zone can cause issues. And for those that are interested, we had an excellent webinar at the end of 2020 just on this matter, on nutrient removal from stormwater. So with the Filtera, again, the Filtera driving head is measured from the outlet invert level, and it assumes a free discharge pipe. And the driving head is measured then from the outlet invert up to the ponding level, the level that we allow the device to pond at before it goes into bypass. So that is the driving head, and as standard with the Filtera, that's 915 millimeters. And we also have a shallow option, which is 695 millimeters. If there is tailwater that acts onto that Filtera, that again reduces the effective driving head. The ponding depth has been met, so from the surface it might look like the device is treating as it needs to, but we have not achieved that full 915 millimeters effective driving head. So that presents an issue. Of course, sites in Christchurch, sites that are very flat, sites that have a very shallow connection or that maybe are doing curb discharge, it's not always easy to completely mitigate the effects of tailwater on a proprietary treatment device. Ideally, we would design so there's no tailwater acting on the treatment device, but sometimes tailwater can be acceptable with a few conditions. The first one is that there is no tailwater occurring onto the filter during the water quality event. Really important that when we're designing the filter to treat that first flush, that it can treat at the design flow rate. We want to limit the tailwater to being as infrequent as possible whether that's going to be to either the 2, the 5, or ideally the 10-year event storm, only then having that condition of tailwater. We want the drain down time to be a few hours, not a few days. Again, that helps prevent biofouling and clogging of the media. And ideally, if there is going to be tailwater, we want to help review that and help step you through the process of making sure that the treatment performance and then ongoing operation and maintenance of the device will work as we need to. So we can design to accommodate tailwater, and there are a few ways to do that. So if we take, for example, this rough cross section through a very simple stormwater network, we have a catch pit that's going to a filter that is going to a tank, and then there is a council connection that is a set invert. So this is the level that the water needs to get to within the storm filter for the device to operate. But of course, as the water is treated by the storm filter and flows into the tank, the level in the tank will build up, and then that will cause a tailwater condition onto the storm filter. So one way to mitigate that is to lower the discharge invert. Sometimes that's not possible, but is to maybe change the tank design. Can we lower the tank to below the storm filter outlet invert to minimize those tailwater effects? Of course, shallower tank is a larger footprint, and that might not be viable from an engineering or commercial perspective. So the other option we can look at is to raise the treatment device. We can use smaller cartridges. We can go for a non-traffic solution. There are a number of ways that we can look to make the device shallower to avoid tailwater from a downstream structure. But of course, the moment we bring the device shallower, there's now water that is surcharging the upstream network. So we do have to make sure that if we are raising the device, that we're not going to surcharge upstream, flood a car park, that we are achieving acceptable depths there.
So a treatment system can be installed in an online or offline configuration. Now, historically, all systems used to be installed online, where all the higher peak flows goes through the treatment system. But remember that the treatment system is typically designed for only to treat the water quality volume or the water quality flow. But the network reticulation itself is designed to handle up to the 10-year or sometimes even to the 100-year peak flows. So when there's high peak flows going through the treatment system, there's some risk of it resuspending some of the sediment that that have settled down. It can maybe even damage some of the treatment system's treatment mechanism, and even for biofiltration systems, especially, it can start scarring some of the media. So to manage these peak flows, we need to put the treatment system offline. So the definition of an offline design is really to only have the water quality flow going through the treatment system, and we have the higher peak flows up to the 10 or the 100 years bypassing around the system. And this is really the best practice for all stormwater treatment devices, whether it's proprietary or a conventional treatment system. And some councils, especially in Auckland, now requires all proprietary devices to be offline. And some other councils have started to follow suit as well.
I think it's interesting to add there that Auckland Council writes within their proprietary device evaluations that the proprietary treatment devices need to be offline, but Christchurch City Council in their Waterways Wetlands Drainage Guide, which is quite old now.
Yeah, yep,
quite old now. Their wetland design also has provision for peak flow bypass within their green infrastructure. So it's whilst required for a lot of proprietary devices, it's also best practice for not proprietary devices too.
So some of the advantage of putting offline, of course, it is to prevent some of that sediment getting scoured, making sure none of the media in the biofiltration system getting scoured. But the biggest advantage of that is also to reduce the driving heat during these higher peak flows. Of course, they will sometimes cause a surcharge to your pipe network, but if you have this external bypass weir outside of the treatment system, you can make that weir as long as possible in order to reduce the driving heat required to discharge the higher peak flows. And it is definitely one of the important design component around the treatment system to ensure we prevent any flooding on the upstream network.
So applying that then to how do we, say for Auckland Council, how do we design a treatment device to be offline? And the answer, or one of the first answers, is to have an upstream structure that has the diversion and the weir included. So here you can see water from the site flows to the collecting manhole. We then have in this case, the jellyfish, which is configured off the main line. It is offline. And there is a weir that is placed in that upstream manhole that is set at the driving head level of the jellyfish. So the level of the water within the jellyfish that we need for the device to operate at its design treatment flow rate, water will preferentially flow to the jellyfish. And then in the peak events, water can overtop the weir and scoot straight out and bypass the jellyfish. So what does that look like in section? So here we can see on the left, we have the collection manhole, the bypass manhole with the weir in. Then we have the jellyfish configured offline. And you can see here that the difference in elevation, the fall through the device, is much smaller than the design driving head of the device. So as water starts raining, water starts flowing to the system, it preferentially flows into the jellyfish, and then it keeps flowing to the jellyfish until the driving head level is reached. And that is when the treatment device is operating at the design treatment flow rate for the water quality flows. If it keeps raining, flows in excess of that can then bypass over the weir, therefore skipping around the treatment device. That's one way of doing it, but requires a couple of additional manholes. So it's something that we offer with the storm filter, both in the manholes and within the vaults, is we have an offline design within one structure. So we still have the collection and bypass chamber. We still have the treatment chamber, and they're separated by an internal baffle wall. And we still have the peak flow diversion weir. And if we compare that to the separate manhole offline design of the jellyfish, you can see then the similarities. One advantage of this is it's much easier to fit into tighter sites. It's one structure rather than three structures to procure and install. So we've got to consider how do we design stormwater treatment devices? What are the ways to go about designing stormwater treatment devices? We have an online design tool, but the online design tool can't take into consideration all of these factors and all of the site-specific considerations. The other thing to consider is that the hydraulic design and integration of stormwater treatment devices, both proprietary and otherwise, is not written into the guidelines. Without guidelines and without approvals that specifically talk about the hydraulics and the hydraulic limitations of the device, it's very difficult to design with that in mind. So if there is product approval, make sure that the hydraulic considerations and limitations from that product approval are put in place. For example, in Auckland, designing offline. When you approach us, Stormwater 360, for assistance with looking at your treatment design, we'll ask you for what are the treatment requirements? Is it standard treatment using a storm filter? Do we have metals to consider? Maybe it's an industrial yard, a car storage yard. That helps us select the type of device that we need to look at. Then we'll ask you what the catchment areas are to work out the treatment flow rate and the 10-year flow rates. That works us out what size is the device going to be. All of our devices are scalable, so we need to know what size we're looking at. We'll ask for the available depth to invert of both the inlet and outlet, because that lets us know how shallow your pipe network is and the available depth that we have to fit in. We'll ask if there are driving head constraints. If we make the device really shallow, are we going to surcharge an upstream catch pit and potentially flood a car park if we've not considered a reduced driving head on that shallow device? And we'll also ask about the downstream water levels. Is there a tank downstream? Is there a swale downstream that we're discharging into that has variable levels depending on the water in the swale at that time? And we can, and we will always advocate for good integration of proprietary devices into your network design. Without good integration, that's where we can lead to problems and operational problems down the track. So a little review of the presentation, and keep in mind, if you do have any questions, please put those into the chat part of the Teams meeting. In review, we've covered the hydraulic principles. We've defined what driving head is. We've defined elevation head or physical drop. We've defined what headwater is and tailwater and how they can be used to manipulate treatment device outcomes and can affect treatment device outcomes. And we've also considered peak flows versus treatment flows and how to manage those within the network. For each of those hydraulic principles, we've applied them to proprietary treatment devices and thought about what happens if we just put in a treatment device and don't consider the hydraulics. Stormwater 360, we go to great lengths to make sure that any device that we recommend will properly integrate into your stormwater network. And ultimately, ask us. We are here to help. So look, thank you all very much for your time. Now we have a few questions here, and I'd encourage more questions to go in. So I think first off, let's start with what the question that Leo has asked here. So Leo has asked, how does treatment quality or capacity being monitored by local/regional councils that the system is designed for? Kevin, I think that would be a good.
Really
It's that's a little bit of a Pandora's box here.
Yeah, that's probably more appropriately answered by the local regional councils we might have in the participants. But a lot of the time, they're probably to monitor that, they usually will have to put in some sort of a rain gauge system usually, or they would put in a flow monitoring system. Then they will see if the system is actually designed for that it will meet what it was designed for. And probably a lot of rather than monitoring it, what's most important is, especially for proprietary treatment devices, is the approval of the system and the standard it was tested for, that it has the condition and it actually shows what each treatment system is approved for and the flow rate it was approved for. And then the local councils will be more than happy to understand what they're installing it and how it can be designed to the site.
And I guess, you know, from a council's perspective, if you're looking to see compliance, is if there is a product approval process that has hydraulic limitations, is the device designed as per the recommendations within the product approval? Has the device been maintained? And then that really allows you to assess if the treatment outcomes are being achieved without having to go and specifically monitor. Just to reiterate, if you can type in the questions into the chat box, that'd be really great, and then we can kind of answer those. Kevin, I guess you know, one of the questions that we get asked a lot is, you know, what do we do for, you know, really shallow sites? Because a lot of the times the council network is either installed very shallow or we've got to achieve a curb discharge. So how might, from an engineering perspective, we go about thinking, what are we going to do for very, very shallow and tight sites like that?
I guess it is all a combination of, do talk to us first. Of course, it is a combination of putting our treatment system where there are different depth requirement and different hydraulic requirements that we could use on tight sites, especially on with tight hydraulic requirements. And we do need to look at how does that effective driving head for the treatment system affect on the upstream network, just to make sure that it's not going to flood, anything like that. So yeah, there's quite a few considerations that we need to look at, especially in Christchurch.
Especially in Christchurch.
Especially in Christchurch.
Ali has an interesting question, which I guess stems from one of the earlier slides in the presentation where we talk about the types of contaminants. And it's not directly related to hydraulics, but it's still a really interesting question. The contaminants that I brought up, if you remember that slide, were there was oils and hydrocarbons, which we try and separate. Then there was litter, everything greater than 5 millimeters. So something like our litter trap will be good for that.
Yes.
Then coarse sediment, which is kind of 110 microns and up. We use a GPT.
Yes.
Filtration achieves kind of the standard and finer sediment. And then we talked about metals and nutrients using typically biofiltration, especially for dissolved metals and dissolved nutrients. But Ali's question is, are there any treatment devices for pathogens?
Pathogens. Ooh, that's interesting. Okay. Pathogens. You really need to use a living or a biofiltration system. Especially our Filterra system has been tested for removal of pathogens, because the biofiltration or green infrastructure system, they really need to have that living, this bioorganism happening in there. So when this harmful pathogens go in there, it can be removed. And what it does, the plant will actually take it up as a nutrient, and it actually has its own living organism that can, in a way, act as a predatory action to a lot of these harmful pathogens. If you are installing a typical media filter, what happens is it actually can remove pathogens as well. But over time, when, in a very moist environment, there's water there, these bacteria or pathogen will end up multiplying to some degree. And over time, it can actually start bleaching it after a little while.
So we've had an interesting question here from Selva. Thanks to that question, Selva, which is, are we aware of any projects where a Stormwater 360 unit was accepted and installed on a new public road? Now, the answer, Selva, is yes. We've supplied lots of treatment devices up and down the country for publicly vested assets, both local roads, state highways, motorways. But the acceptance process really depends on the asset owner and who that device is being vested to. Now, each road controlling authority and local council will have their own requirements, both for how to design. I think a really good example would be Auckland Motorways has a very specific design requirement for proprietary treatment devices that it will be vested to the Auckland Motorway network. But it really then is a conversation around the specifics of where in the country is this project and what are the treatment requirements and outcomes needed. So Selva, that's something that we'd absolutely love to have that conversation with you after this, just knowing that we've supplied proprietary treatment devices across the country for public road assets. An interesting one here from Anand on what is the maximum flow it could treat, and it's suitable, and is it suitable for a citywide system? I guess before, I mean, the first thing to say, Anand, is the treatment devices that we have, they are absolutely scalable, whether that's from one cartridge to many, many cartridges. And I'll just let Kevin briefly talk about a couple of catchment-wide treatment devices that we've installed.
Probably the biggest system that we have is the one in Christchurch, treating the Bells Creek. It has about 570 cartridges for treating runoff from citywide, both residentials and commercials, and the roads for the citywide system. Yeah, so it is definitely scalable to any size you need it to be.
And I think from a hydraulic perspective, as this is a hydraulics webinar, the great thing by having a modular system in the way that, say, the storm filter operates and how we design the jellyfish is the hydraulics are not overly impacted by scaling from 1 cartridge up to 580. There are still some considerations and there are safety factors that we have to play with. But ultimately, the driving head for a 69 centimeter cartridge is 770 mil, whether it's in whether there's 1 cartridge or a much larger system. So there may be additional factors and additional depths that mean we go up to maybe about 930 mil for the larger volts, but it scales without a huge impact on the hydraulics of the system as well, which is quite important. An interesting question here from Morel. Is there a general guide from Stormwater 360 about selecting a proprietary device based on constraints to help with early scoping? And then goes on to ask, also, how does whole of life cost vary across different treatment devices, assuming constraints are the same? So I think there's kind of 2 parts to this question.
Yep.
I'll maybe talk about the device selection, and if you want to talk about whole of life costs.
Yeah, sure.
So generally speaking, one of the easiest ways to go about going, well, what device do we need, is just to get in touch, especially if it's a non-standard design or you're in an area of the country that doesn't have a rigorous proprietary device evaluation process. If there's no product approval process, it's maybe hard to know where to start. And depending on where you are in the country, there might be different treatment outcomes that are needed and different treatment preferences that are had by the local and regional councils. So in the first case, I'd always say, look, come to us. It shouldn't take us too long to provide you with an answer. There is also our online design tool, but a lot of times the online design tool will have a very small number of device configurations rather than the full gamut of multiple cartridge heights and everything. So if you you have a site that has some constraints, whether that's from a treatment perspective, an asset ownership perspective, or a hydraulic perspective, then do get in touch.
Yeah.
And with regards to whole of life costs, we've done some work on life cycle costs.
Well, it is, and also I just want to add a little bit more on in terms of its constraint. There's definitely different constraint in terms of physical constraint itself, or maybe you're trying to put it in a existing network, or there could be a hydraulic restriction to the upstream of the treatment system, or there could be a hydraulic restriction from downstream of the treatment system. So we have a whole raft of selection of treatment device, and that's the reason to be able to fit into all these different restrictions. And that's the reason why we have a lot of these options. Jellyfish might be better for some of the hydraulic restriction on the upstream network because it has the lowest driving head requirement. But again, storm filter might be able to fit within the network if there's a restriction from downstream of it as well. You could even use a Filtera system to maybe look at just doing an overland flows and treating it, at source. So again, it really depends on this, what's restricting you on that site. So it's best to really just come to us.
Yep.
And when it comes to life cycle costs, again, it really depends on what we can fit into that restrictions. And they all have different advantages and disadvantages in terms of its maintenance requirement, and also who needs to do the maintenance, and especially locations might make it a little bit difficult for a specialized maintenance contractor to go to. We may be able to put in a Filtera system, which means, a local landscapers might be able to maintain it. And that way you could, the life cycle cost will vary very differently depending on which hydraulics restrictions you have on your site, and how we can choose and for our treatment system.
And it's a question that we'll more than happily talk about with both yourselves and the asset owners, because you know, a single storm filter treating 500 meters squared might have very different life cycle costs in two very different catchments.
Yep.
Depending on the catchment. So it's a question that we can have. Kind of on that, Sarah has asked, do we have a best contact person regarding technical questions? Yep, you could email either Kevin or myself. I'll be sending out links and the hydraulics paper after this presentation, so tomorrow morning, and then feel free just to get in touch with us on that. Question here from Arsini, which is an interesting one, and Arsini, you always throw curveballs our way. Love it, absolutely love it. Arsini says that she can understand the technology behind the TSS contaminant treatments. Can you please clarify how the total petroleum hydrocarbons in oil and grease is treated? And lately she's noticed that industrial sites with high
BOD,
high pH are suggesting to use these devices. Right. On what basis, Kevin?
Okay. So it really depends on what treatment system we use, but a lot of the media treatment system will physically remove it, especially, you know, like our storm filter system will have the perlite to absorb some of that oil or grease, anything like that. Same with the Filtera, the mulch on top will absorb some of that oil as well. But in industrial places, these oils or grease are in a much elevated concentration compared to what the systems are actually usually designed for. Now, these systems are remember, they're designed for, you know, standard car parks or standard roads, things like that. So when you apply it to industrial areas, we typically would put it in a treatment train where we will have a oil water separator, which will focus on removing this oil and grease before it gets to the media treatment, which then it can focus on removing either the coarse particle, which we can install a gross pollutant trap to concentrate on removing that as well. And this media treatment then can concentrate on the finer sediment. Or we can install another media treatment, such as zeolite, that can concentrate to remove the dissolved metal as well.
Yeah, so there's definitely ways to design, but again, it's important that good process, especially for industrial sites, which I know I've seen that you have quite a focus on, that there is really a good evidence-based approach to support that the devices proposed will achieve the outcomes, and strong, rigorous testing evidence, usually from overseas processes, especially the American test certificates, both Washington and New Jersey, are very rigorous. So designing as per those test protocols could really provide a bit of a guarantee. Now, our last question, of course, if there are any questions for further and beyond this, then please do get in touch. We're always happy to take some questions. But our last question comes from Fred, which is quite a nice way to round off the presentation. Just thinking about treatment devices in general is around their maintenance. It's all very well using a vacuum cleaner, but if you don't empty the vacuum cleaner, at some point it will stop working. And it's just the same for stormwater treatment devices. They always need maintenance. No matter how much you don't want to provide a maintenance budget, they'll always need maintenance. So Fred asks, does Stormwater 360 provide a maintenance servicing team for its devices, or is it the sole responsibility of the asset owner? Maintenance itself and organizing the maintenance is going to be the responsibility of the asset owner. We don't own the devices, and we're not also in a position to enforce compliance and enforce maintenance. That is, councils will have to enforce the maintenance of the devices as part of their compliance monitoring. Something that Stormwater 360 does, though, throughout both the design and then operation stage is advocate for good maintenance outcomes. It's only with good maintenance of any stormwater device, whether it's a proprietary device, a rain garden, a swale, or a pond, that device will function and provide that environmental protection that it's been designed to. The other thing that we do is we do work quite closely with maintenance providers to help facilitate that maintenance. So Stormwater 360 ourselves, we don't do the maintenance ourselves, but for our cartridge devices, we have a training program that maintenance contractors can go through that training program and learn how to do the maintenance and become certified. Things like the storm filter cartridges, they have a lifetime warranty. So that the maintenance process involves the cartridges coming back to us, we refill them, and then we send out a new cartridge to keep that lifetime warranty. That's quite key. It's a good environmental practice to have a circular economy for these things. And so we keep, reuse, refurbish cartridges as we go along. For devices like the Filtera, we don't need a specific maintenance contractor to do that, because with the Filtera, it's simply replacing the top 75 millimeters of mulch. The media and the plants shouldn't need replacing under normal conditions. And in those instances, we've trained up contractors, we've trained landscape contractors, we've even gone along to Marae in schools and trained them on how to do the maintenance of their biofiltration devices, and they use that as a good learning mechanism. Maintenance of all devices is really important, and it's really no one's sole responsibility. It's not our responsibility, it's not the asset owner's responsibility, and it's not the council's responsibility. It's a shared, combined responsibility to the environment to make sure that our treatment devices are maintained, and we do as much as we can to help with that process. So thank you all so much for your hour of time today. I realize that with a lot of the events that have gone on across the country, that everyone who is already strapped for time is even busier. Hopefully you found this presentation and webinar useful. A copy will be made available. I will send around a link to the recording, along with a link to Kevin's paper that I referenced earlier on. As I say, if there are any questions as an ongoing from this, please do get in touch with Kevin or myself, and we'd be more than happy to have a chat with you guys. Thank you all.
Cool. Thank you. Cheers.